So to start this unit, we're going to take a look at the differences between ionic and covalent compounds. Now, we just spent the previous unit looking at ionic compounds. We realized that we always have these metals. We always have a metal who's looking to get rid of an electron, maybe two. So maybe we have a +1 charge, a +2, or even a +3 charge. Those guys are trying to get rid of electrons. And where are they going to go? Well, they're going to head over to these nonmetals. And the nonmetals are going to gain 1, gain 2, or gain 3. And everybody's going to end up with an octet, and everybody's going to be happy. So we have these metals that don't really want those extra valence electrons. They give away 1, 2, or 3. We have nonmetals who want more valence electrons. They might be 1 short, or 2 short, or 3 short of getting their octet. So the metals hook up the nonmetals. The metals give those electrons to the nonmetals. Now, when you give away electrons, if you start off equal, protons and electrons, and you give away electrons goes down, we have fewer electrons. That means we have more protons. So if you give away electrons, you're going to have positive charges. And the flip side, if we do the opposite, if instead of starting off equal and losing electrons, now we're going to start off equal but then gain electrons. And now we have more electrons than we had to begin with. So we're going to end up with more negatives. That's why we end up with negative charges. So when we think about ionic, we should be thinking I give, or, if I give it's a metal, or I get, that's a nonmetal. So we have to have this kind of complementary system. The metals will give up electrons, the nonmetals get electrons. Now we call the metals a cation. Remember, a positive cation and a negative nonmetal. So the cation is attracted to the anion, and that's actually a very, very strong attraction, but that keeps them together. Now just think of the electron cloud here attracted to an electron cloud here. Here's your metal, here's your nonmetal, and the electron clouds are attracted because one's positive, one's negative, just like two magnets would get stuck together if you brought them near each other and they were oppositely charged. Now, covalent compounds, this is the new stuff. Covalent starts with CO, cooperate starts with CO. So when we talk about covalent compounds, we're actually talking about nonmetals. There's no metal in the picture anymore. So if you see a metal, it's automatically ionic. But if you don't see a metal, if it's just a bunch of nonmetals, they're going to cooperate. They're going to share their electrons. One of them's not just going to give up electrons to the other. They're going to pool their electrons together, and they're going to divide them up and share electrons. And when they do that, everybody's going to get a full outermost energy level, and everybody will be happy. And that happens in both situations, ionic and covalent. Everybody gets happy, but they accomplish it different ways. Here you completely give up, or you completely get electrons, and here we share electrons. Now, how do you know if something's ionic or covalent? Just by looking at it. First thing you should do is look for a metal. If you see a metal and a nonmetal, it's automatically ionic, because that metal is going to give electrons to the nonmetal. So if you see a metal, it's ionic. Then you have to worry about charges, you have to worry about Roman numerals, you have to worry about polyatomics, you have to worry about crisscrossing charges, all that fun stuff that you did in Unit 5. But if you look at all the elements involved and there's no metals, if there's all just nonmetals, then you know it's covalent. The other way is by looking for prefixes in the name. So if you have a name, just check it out, see if there's some prefixes in there. If there aren't any prefixes, then it's automatically ionic. Now think about everything we've done up to this point. Have you seen a single prefix? Sodium chloride, magnesium sulfide, magnesium sulfate, sodium phosphide, potassium bromide. No prefixes. Now what do I mean by prefixes? Well, what's this? Carbon dioxide. Di is a prefix. It tells us that we have 2 oxygens. How about this one? I bet you know that. Carbon monoxide. Mon means 1, so there's 1 oxygen. So that prefix is giving us an idea about how many of each element there are in the compound. So if you see prefixes, it means it's covalent. It means that these nonmetals have to cooperate, and they can actually hook up in different ratios, which is why the prefixes are so important. It helps us differentiate between different compounds containing the same elements. So real quick, if there's a metal involved, it's automatically ionic. If there's no metal, if it's all nonmetals, it's covalent. You could also look at the name. No prefixes, just like we did in Unit 5, no prefixes. That means it's ionic. And if we see prefixes, it's covalent. And we're going to learn about prefixes in the next slide here, or next couple slides. All right, molecules. Quick little point here. The word molecule should really only be used for covalent compounds. So if you see NaCl, it's really incorrect to call it a molecule. It's more appropriate to call it like a ratio. There's a 1-to-1 ratio. 1-to-1 ratio for sodium chloride. If you have, sodium oxide, Na2O, it's a 2-to-1 ratio. So when we talk about ionic compounds, we really should be just talking about a ratio. But when we talk about a molecule, we're talking about a structure that has a beginning, has an end, and there's a whole lot of atoms that are connected in between whose electron clouds are overlapping because they're sharing electrons. So all of these things here, water is a molecule, carbon monoxide is a molecule, carbon dioxide is a molecule, and this guy here, think you know what that is? That's sucrose. And this is a bigger molecule when you compare it to these other three. But it has a beginning, it has an end, it has lots of bonds. We'll use single lines here to represent bonds. And this is a discrete structure. Whereas over here, you could have a little tiny pile of salt. All the NaCl's are bonded on a 1-to-1 ratio, or you could have a huge pile of salt, and it's still a 1-to-1 ratio. There's really no beginning or end. You could have all the salt in the entire ocean, but that's not considered a molecule. Now, is this a huge deal that you use the word molecule correctly? Not necessarily. No one's going to kill you if you use it when you're talking about an ionic compound, but it's really not correct. So try to just reserve that word for covalent compounds, compounds that have a structure connected with bonds, energy level or electron clouds, energy levels overlapping, sharing electrons, and so forth. All right, so just to preview here, di should make you think of two, atomic, two atoms, and the catch is they have to be two of the same atoms. Diatomic molecules are molecules. Remember, molecule means covalent. They're going to share. So we have two atoms of the same kind that make these molecules. Now these are the elements that do it. Hydrogen. Here's H. H hates to be all by itself. So if hydrogen gas is produced, it's H2. Nitrogen hates to be by itself. So we end up putting them together. And we're going to see how that works out in a little while. But N2. O, oxygen hates to be by itself. So if there's nobody else to bond with, it hooks up with other oxygens and makes O2. So right now, you're inhaling O2 molecules. And you're inhaling N2 molecules. Because about 78% of what you're inhaling is nitrogen. And 21% is oxygen. Anyways, fluorine makes F2. Chlorine is Cl2. Bromine, Br2. And iodine, I2. Now, there are 7 elements that do this. And it kind of makes a 7 on the periodic table. These 6 elements plus this guy over here. So it looks like a 7. What I would do if I were you, and I had a periodic table that I used all the time, I might lightly shade in or lightly highlight these elements. So I remember that they always hook up in pairs. So diatomic molecules, again, it's going to become really important later on that you remember this. But right now we're going to learn how these molecules are formed. So, naming compounds. Remember earlier we said if it doesn't have a prefix, then it's ionic. If it has a prefix, then it's covalent. So let's start off with ionic. Ionics have a set ratio depending on their charge, so you really don't need prefixes to give you a clue about what the formula is. We wouldn't call this sodium monochloride. We wouldn't call this disodium oxide. This is just sodium chloride and sodium oxide. So anybody who knows anything about chemistry, if you say sodium chloride, they automatically know sodium makes a +1 charge. It's the only option. Chlorine makes a -1. That's a 1-to-1 ratio, so therefore it's NaCl. And if you say sodium oxide, again, anybody who knows anything about chemistry knows sodium's +1 and oxygen's -2. So when you crisscross those charges, it's Na2O. That's your one and only option for sodium oxide. So you don't need prefixes. No prefixes, because there's no other options. Now, covalent compounds. These are different. Covalent compounds can cooperate, or they could share electrons, and they can make different ratios. Because they have so many options, and we keep using the same elements, we have to use some prefixes. So you guys are familiar with carbon monoxide and carbon dioxide. That mon or that di tells you how many oxygens there are in the compound. Take a look at this dihydrogen monoxide. Look at this terrible substance. Death by inhalation, corrodes metals, causes bloating and nausea, can cause electrical circuits to short circuit, can cause tissue damage and burns, soil erosion, brake failure, disaster, destruction, and so forth. This terrible, terrible substance. Take a moment, look at the name, think about what you know already about prefixes, because I bet you know some stuff. What's the formula for this compound? This terrible, terrible compound? Doesn't di mean two? Two hydrogens? As a chemist, we write H2. And doesn't mono mean one? One oxide, one oxygen? Isn't that just plain old water? Now, nobody calls dihydrogen monoxide, or nobody calls water dihydrogen monoxide, but you were able to figure that out if you knew a little bit about your prefixes here. All right, let's move on and let's look at some more serious compounds. So here are the prefixes that we're going to be using. Now, we'll give you a list of these prefixes, but I bet you know a lot of these prefixes already. For instance, you know carbon monoxide, so you know mono means one, and you know carbon dioxide, so di means that there's two oxygens. You all know tricycle, triangle, there's three corners for a triangle, so tri means three. Tetra, did you ever play Tetris? Every shape is made up of 4 blocks. Tetra means floor. So think about all the different shapes for Tetris. That's why it's called Tetris, because tetra means 4. So maybe you got to study that guy here. Now, pentagon's got 5. Hexagon's got 6. Hepta, maybe you got to study hepta. Hepta means 7. Octa means 8, just like an octopus. A nonagon has 9 sides. Maybe you got to study that one. Sometimes kids mix that one up. And finally, deca, decade. You guys are all familiar with the decade being 10 years. So that dec should make you think 10. So yeah, it might be a little overwhelming here, but you're going to use this so much that you'll get used to them. And there's really only 3 that you probably have to devote some time to study. And maybe you know some of those, so maybe you have to study fewer than the 3. But either way, you're going to have to use these to be able to name compounds and to write formulas. So let's talk about naming compounds. What we're going to do is a lot of what we've done already. Think about NaCl, sodium chloride. Sodium. We left the name of the first element alone. We just said sodium. The only difference here is we're going to add a prefix if there's more than one. The second element, chlorine, we changed to chloride. We still do that. We're still going to change the name, the ending of the second element to "ide." The only catch is we're going to add a prefix. So the first element, just leave it alone. Add a prefix if there's more than one. The second element, change it to "I," just like we've been doing, and then throw a prefix on. Now this is ionic, so we're not going to do that. We're not going to use prefixes for that. But let's talk about here, P2O5. The first element is phosphorus. So I'm just going to say phosphorus, but there's 2 of them. So it's diphosphorus. Diphosphorus. And then I'm going to look at the second element. Now that's oxygen. I'm going to change the ending of it to "ide," just like I did before. So it's oxide, but I'm going to add a prefix, penta. Pentoxide. Now there's one little catch here, and we're not too worried about this. This will come with time. The more familiar you get with these compounds, the more likely you are to do this correctly. Again, don't sweat it if you're not catching on to this part right away, but things will start to sound correct. If you have an O or an A, if you have those 2 vowels next to each other, because the prefix ends with 1 and the element starts with 1, if that's the case, then drop one of those vowels. Like everybody says, carbon monoxide, not monoxide. Those 2 O's next to each other kind of sound silly. So we drop one of them, and you drop the one on the prefix. So it's monoxide. Over here, pentoxide, it's really penta, but then you would have a penta, A, next to an O. So it's just pentoxide. Again, is that a big deal? If you say pentoxide, is anyone going to going to take off points? No, but you'll start to learn what sounds correct and what doesn't over time. All right, let's move on. We got N2O. You might have gone to the dentist. They might have given you laughing gas, kind of relax you a little bit. The appropriate name for that, N2, nitrogen, and throw a prefix on. Notice the ending's not changed here. And then the second element's oxygen. So it's oxide, and you put the prefix mon on. So dinitrogen monoxide. Cl2O8. There's two chlorines, so it's dichlorine. We don't change the ending of the first word. But then the second element's oxygen, so it becomes oxide, and there's 8 of them. So it's oxide. And again, this might sound right to you over time. You're going to drop that A. It's not oxide, it's oxide. Get rid of that A. All right, let's try some out here. Use the prefixes and write the formulas. We'll stop for a minute. Notice there's no prefix here, so we assume it's just one. But use all these prefixes and write the formulas, and then I'll come back on and we'll take a look at your answers. All right, so dinitrogen. You should have gotten N2 tetroxide. O tetra is 4, so N2O4. Now there's no prefix before boron, so that means it's just 1. Boron, and then tri means 3, trichloride, so it's Cl3. Dinitrogen, N2, trioxide. Tri means 3, so it's O3. Notice that these two, same elements, different ratios. Covalent can do that. They're tricky. All right, phosphorus pentachloride. No prefix in front, so we assume it's just 1, P, and then penta's 5, Cl5. And finally, iodine, no prefix in front of it, so it's just I. Fluorine is changed to fluoride, and hepta means 7, so it's IF7. So these guys, I really like covalent compounds. I love having those prefixes there because I don't have to worry about charges. I don't have to worry about crisscrossing them. I don't have to worry about Roman numerals or anything crazy like that. It's just whatever those prefixes are, that tells me how many of each element I have. Now let's do the reverse. All right, so now we may have to look back at the prefixes so we can write these names. The first one nitrogen. So you're just going to write plain old nitrogen. We don't use the prefix mono if it's the first element. Like nobody says carbon or monocarbon dioxide. It's just carbon dioxide, not monocarbon. So whenever the element comes first and there's only one of them, you just write the name of the element. So it's nitrogen, and then chlorines, there's 3 of them, so trichloride. Trichloride. The next one, there's 2 chlorines, so it's dichlorine. Check your ending, make sure it's not ide, it's ene. Dichlorine. 7 is hepta, and then it's oxide, so I'm going to drop that vowel, hept, oxide. The next one, 2 nitrogens, dinitrogen, and then there's 4, tetra, and then hydrogen is hydride. Now, hydride is not the same as hydroxide. H is hydride. Make a little note in your paper there. H is hydride. OH with a -1 charge is the hydroxide ion. They are 2 entirely different things. This is 4 atoms of hydrogen, tetrahydride. This, OH, is a hydroxide ion, and that hooks up in ionic compounds, not covalent. So we're not dealing with hydroxide ions. All right, I stands for iodine. And dioxide for the O2. And finally, this is silicon, not silicone. Silicon. And chlorine, there's 4 of them, so it's tetrachloride. So silicon tetrachloride. All right, so you're going to get some more practice with this. You're going to have a handout where one side you're going to be using the textbook to just kind of review everything that I just spoke about, and then the other side you're going to flip it over and you're going to do some practice. And then we'll meet up again and we'll do some covalent compounds. We'll draw them and make them models and figure out what these structures really look like in the real world.